Let's talk about how we measure the amount of radiation around us, the amount of ionizing radiation that we come into contact with. So there's two different ways that we can do that. There is the passive way of measuring radiation, and then there's a more active way of measuring it. Dosimeters, which is what you would wear if you worked in some kind of a vocation where you're working with radioactive materials or something that produces a lot of high energy radiation, like if you were an X-ray tech or something like that, you would wear a dosimeter on your person at all times while you're working. And what the dosimeter has inside of it is actually just photographic paper. I believe it is slightly specialized, but it is essentially photographic paper inside of the dosimeter. And when you're exposed to high energy radiation, the film, that photographic film, becomes developed. Because if you remember, high energy radiation can pass through matter. It can go through things. And so even though the film is inside of this plastic sheath, so visible light can't get to it and develop the film because visible light isn't energetic enough. Things like X-rays, things like gamma rays, beta particles, things like that have enough energy they can pass through the plastic, impact that film, and develop it. And so the badge is just passively measuring over time how developed does this film get, because the more developed the film is, the more radiation you have been exposed to. Now the flip side of that is a Geiger counter, and this is more active measuring of radiation. The way a Geiger counter works is you have some kind of inert gas, usually it's argon, inside of a container here that has a thin film on one end, so it is sealed, so the argon can't get out, but it's a relatively thin piece of glass or something like that that radiation can get through. So when high energy radiation goes into this container here and it impacts one of those argon atoms, it's going to ionize that because it has a lot of energy. And so when that high energy particle, whether it's a beta particle, alpha particle, or a photon, when it smacks that argon atom, it's going to knock some electrons off of it. Those electrons are then attracted to the voltage that's applied to the post here in the middle of the container. And so the electrons go to that and they are detected. And so in the movies, or if you have a Geiger counter yourself, which by the way, they're actually not all that expensive. If you want to go and try and get one yourself just to kind of have some fun with. The really fancy ones are expensive, but you can find relatively cheap ones. And by relatively cheap, I mean like 50 to 100 bucks. That ticking sound that you hear, if you have a Geiger counter that gives an audible notice that it's detected something, it's actually the detection of the electrons that you're seeing or that you're hearing there. And so the idea is that because there were electrons that were detected, they had to come from somewhere, and so they were produced when high energy radiation knocked them off of the atom they were on in the first place. And so that is how a Geiger counter or a Geiger-Müller counter works. Moving on from that, let's talk about the kinetics of radioactive decay. Thankfully for us, unlike the kinetics chapter where we had zero-order reactions, first-order reactions, second-order reactions, and then there were some even weirder ones, nuclear decay is only ever first-order. It is always a first-order process. And so because of this, we only have to worry about one method, essentially, of calculating this kinetics data. And so this equation here, this is actually the same equation that we saw before. This is the integrated first-order rate law. It's just had a little bit of algebra algebra done to it. If you go back to the kinetics chapter, this was one of the options. This was not the normal one that we would use, but this is one way to rearrange that equation. And so this is telling us that the natural log of the number of isotopes, the number of atoms at time t, divided by the initial number is equal to minus kt. And remember, the k here is the rate constant, and then t is just the time. It's how much time has passed. So the n sub t, the number of atoms at time t, that's how many are still there. How many have not yet decayed. And n0 is how many you have to start with. Another way of talking about kinetics processes in chemistry, if you remember, was the half-life. This is something that we talked about in the kinetics chapter. We were looking at the half-lives of different reactions. And this is actually the most common way of discussing the kinetics of radioactivity and radioactive isotopes. If you've ever watched, I mean, there's lots of movies where they'll have radioactive stuff and they'll be talking about the half-life of this or that. The half-life, just to remind you of what that was from the kinetics chapter, that's the amount of time that it takes for half of the stuff that you start with to react, which in our case would be to decay, since that's the process that's happening, is a decay. So the half-life of a material is how long it takes for half of those isotope atoms to decay into something else. We don't really care what it decays into or even how it decays, whether it's alpha, beta, whatever. We just care how long does it take for half of them to decay. And so we can use this equation to quantify that. So the half-life is equal to 0.693 over k. And again, because all of them are going to be first order, we don't have to worry about the second order half-life, if you remember those, where the concentration comes into play. No need to worry about that here. It is only first order. And this is just an illustration of what's happening here. It's kind of similar to what we did in the kinetics chapter once again. So if you start with 10 grams of strontium-90, strontium-90 has a half-life of 28.8 years, so pretty decent half-life. That's quite a long time, from a human perspective anyway. So after 28.8 years, you wouldn't have 10 grams, you would only have 5 grams left. After another 28.8 years, it's not that another 5 grams goes away, it's half of what you had the previous time goes away. So it's not you lose 5 grams each time, it's half of whatever you have goes away. And so we started at 10, we went down to 5, then down to 2.5 here after 40, well, that'd be 56-ish, 57-ish years. Another 28.8 years, and now we're down to 1.25, I think that would be, yeah. So just every half-life, half of whatever you had is gone and decayed away. And this can vary hugely, absolutely hugely, from one isotope to another, especially when it comes to naturally occurring isotopes versus man-made isotopes. Naturally occurring ones tend to have much longer half-lives, and if you're confused as to why that's the case, if you stop and think about it, if there was a naturally occurring isotope that only had a half-life of 3 seconds, do you think we'd find any anywhere? No, it's gone. Like, as soon as it's made, it's gone. So the naturally occurring isotopes, the stuff that we can go out and find in nature, it's almost exclusively going to have half-lives on the order of years, at least. Sometimes, there might be a few things that have, maybe a few days half-life, and so, if we have the stuff that they're being produced by, because usually there's something else that decayed and turned into this thing that only has a few days worth of half-life. So if we have that original stuff as a sample, we can detect that other stuff. But in terms of just going out there into the wild and finding some radioactive elements, essentially everything you find is going to have half-lives on the order of, if not hundreds or thousands of years, then billions of years. So as you can see here, thorium-232, which is the most common isotope of thorium on the planet. And there's quite a lot of thorium on the planet. Not as much as like iron or something like that, but there's lots and lots and lots of thorium. It has a half-life of 14 billion years. So just think about that for a second. If you had 10 grams of thorium, I believe this entire solar system will be gone by the time that would turn into 5 grams of thorium. Actually, I know that this whole solar system will be gone, turned into a different solar system, and that one will be gone too, before half of your thorium decays. So this has an exceedingly long half-life. Uranium-238, same type of thing, although not quite as long, but it's still 4.5 billion years is the half-life of uranium-238. It is so close to being stable that it is practically stable. Carbon-14, on the other hand, which is another one that is naturally occurring, that has a half-life on the order of about 6,000 years. But the carbon-14 is replenished. We actually make more carbon-14, or at least radiation from the sun makes more carbon-14. And so that's why it is not completely gone at this point. Radon-220. This is the one of the isotopes that could get into your house, as it seeps up from the ground. It has a half-life of about a minute. And then thorium-219, so just 3 neutrons different from thorium-232, it has a half-life of a microsecond. So 14 billion years versus 1 microsecond, the only difference is 3 neutrons. That's kind of crazy. So all these isotopes here are naturally occurring. We've already looked at a few of these up here. Like the uranium here, 4.5 billion years. Uranium-235, which is the more radioactive version. You can see it still has a really long half-life, almost a billion years. Potassium-40, really long half-life as well. And then the carbon-14 we've already looked at. The synthetic isotopes here, some of them have decently long half-lives. So like the plutonium-239, which is synthetic, it is man-made, it does not occur naturally. It still has a pretty decent half-life, 24,000 years. Same thing here with cesium-137 and strontium-90 for that matter. They have a half-life on the order of 30 years. But then iodine-131 is less than, well, let's see, that's 0.022 years. That's on the order of like a few days, I believe. Maybe 10, 20 days, something like that. You can work out whatever that is on your calculator if you'd like. So not seconds, but it's long enough. I believe this is the iodine that they sometimes will use in medical settings, is iodine-131. So you have to, one of the reasons why it's so expensive is because you can't stockpile this stuff. You have to make it and then use it, because if you wait for a few days, it's gone. It's not there anymore. So you have to make it and then use it right away. Let's do an example here. So we have plutonium-236, which is an alpha emitter, has a half-life of 2.86 years. If a sample initially contains 1.35 milligrams of that, what mass is left after 5 years? All right, so I'd encourage you to pause the video here and see if you can work this one out yourself. After you give it a shot, come on back and we'll work it together. Alright, if you remember from a few slides back, this equation can be used to describe any nuclear decay process because all of them are going to be first order, and this is the integrated rate law for first order kinetics processes. So in the question, we're told we're trying to find n sub t, the amount of the stuff that is left after 5 years. That 5 years is t, it's the time that passes. So after 5 years, how much is left? We're also told that we started with 1.35 milligrams. We're not given K, but we do know that the half-life is 2.86 years. And we also know that the half-life, which again is 2.86 years, is equal to 0.693 over K. And so if we do a little bit of algebra here, multiply both sides by K, divide both sides by 2.86, what we will get is, let's see, yeah, so that's my half-life. Make sure I'm doing that right. Yes, okay. So that is going to give us 0.242 per year as our K value, as our rate constant. And so now we have K, we have T, and we have our initial starting amount of the plutonium. So we can solve for n sub t. So I'm going to go ahead and put in what I know at this point. We have negative, let's see, K is 0.242 per year. T is 5 years. So those year units are going to go away. So I'm going to need to do a little bit of algebra here. Let's see here. So I have, let me just multiply these together. So it's going to be negative 0.242 times 5 gives me negative 1.21. I'm going to need to raise e to that value. And I know I'm going to need to do that because I need to get rid of this. Why did I put an equal sign there? That shouldn't be an equal sign. Sorry about that. So it's just the natural log of this. So I need to get rid of that natural log. And to do that, I'm going to raise e to all of this, which is going to turn this into just n sub t over 1.35 milligrams. And so if I multiply both sides by the 1.35 milligrams, I will have my answer. So I'm going to go ahead and raise e to negative 1.21, and then multiply that by 1.35. The amount at time t is 0.403 milligrams. And that number makes sense to me, because the half-life is a little over 2.5 years, and we've gone 5 years, and so we should be not quite to cutting our starting value in half twice, and that number looks pretty good to me for that, just that rough estimate. Right, we're going to call it there for this one. I will see you all in the next video, and we'll talk some more just in general about nuclear chemistry and some of the applications.